So, good morning, guys. The lesson we're talk about is to find the maximum flow and to find the shortest. So, first is we need to find the maximum flow on the transport network given below, or we called graph. So, first is we use the Ford Fulkerson algorithm or its variation, and also the Edmonds-Karp algorithm. So first, the problem setup is the source, sinks, and intermediate nodes. So the source we called is this, the S1, S2, S3, and S4. So, para mas maintindihan, source is S1, S2, S, sorry, S1, S2, S3, and S4. So the sinks we called is the sinks is we call the T1 and T2. T1 and T2. And the intermediate nodes is the intermediate nodes are A, B, C, D, and E. So the source is the S1, S2, S3, and S4. And the sinks is T1 and T2. So the intermediate nodes in this graph is the A, B, C, D, and E. So next is we need to calculate the maximum possible flow from all sources. So the sources is this, the S1, 4, and to all sinks. So where is the sinks is? The sinks is T1 and T2. So we need to calculate the source and the sinks. These two, source and sink. Next is calculate it. So so we need to connect the source with the infinite capacity and we need to create the sink. We need to connect it to the T1 and T2. And the source is the connecting of source is S1, S2, and S3, and also S4. So this two this two is reduces the multi-source, multi-sink problem to a single source, single sink, and network flow problem. Next is the algorithm steps. We need to initialize, or we need to initialization. So we need to start in the zero. Where's the zero? We need to start in the zero. Next is augmenting path search. So the augmenting path search is the residual capacity of the edge and the original capacity minus the current flow. So we need to repeat it or continue until no augmenting path exists from S to T or in the source and sinks. We need to continue it until no augmenting path exists. Next is we need to calculate the maximum flow. So to convert the graph to include S and T or source and sink, we need to use BFS to find path and calculate the flow iteratively. So example of it is S. We need to use BFS or the algorithm steps. We need to add first is example of it is S. Next is the S1. Next is A and TI. T1 and T. So this example is continue augmenting until no path exists. Magko-continue lang ito hanggang wala ng path na nag-exist sa graph. So, next is we need to calculate step by step the maximum flow based on the edges and capacity shown in the image. So the maximum flow in a transport network is 20. Tama, 20. Ang maximum flow in a transport network or in this graph. So, this is calculated by augmenting flows from source until the sink. So, this is the source and this is the sink. So, 1, 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, hanggang mag-20. Kasi 'di ba ang sabi is magko-continue magko-continue lang siya habang may path na nag-a-exist. So this is calculated by augmenting flows from the super source S through the intermediate nodes to the super sink. So source, this. And then intermediate nodes is ABCD, this T1, this is the sink, this is the source. So respecting all capacity constraints. So the final answer is 20. The maximum flow of the transport network given below is 20. 20. This is the answer, final answer. Next is to find the shortest path. So find the shortest path of each node from the starting vertex. So to find the shortest path from the starting vertex S, S, S to all other nodes in the graph, S is S in all the nodes, intermediate nodes in the graph. So the intermediate nodes is the A, B, C, D, and all the letters. So this is we use the Catras algorithm. So we find the step by step of this algorithm. So we need to initialize. So we need to set the distance to the source vertex S to 0. And also set the distance to all other vertices to infinity. Use a priority queue to select the vertex with the smallest known distance. Next is we need to iterate. Extract the vertex with the smallest distance from the priority queue. And we need to update the distance of each neighbor of a shorter path and found. So just repeat the process or continue until all vertices are processed. And the final distance represents the shortest path from S to all other nodes. So the shortest path to call this from S to all other nodes. So the node is these letters. So we need to compute the shortest path. So the shortest path distance from the vertex S to all other nodes are as follows. So first, calculate it. So S arrow, we need to put arrow, pero hindi na kasi para hindi na magtagal. S to S equals 0. This is the starting point. Next is S A. 2. Next, kasi ang shortest path na tinatawag is we need to start and the smallest until the big number. So we need to start to 0. Next is SA. First, we need to S and X, and next is this S and A. So the value of S and A is 2. So 2. Next is S and E. Yes, S and E. Kasi tapos na tayo sa A. So this arrow is nakatutok sa E. Kasi tapos na sa A. This is S, E. 2. So the value of S and E is 3. I no. 5 pala. 5. 5. Ay, tama, 3. Tama, 5. Eh, 2 and 3 plus 5. Kasi S, 2, S, diba, nag-start tayo sa S and A, 2 plus 3. Okay. Next is S and S, 3, 9. 9. S, S, F. 9 din. S, T. 9. S, V. S, 11, 11. S, F. 14. S. So this is we call the shortest path. So you can see we start to the 0. To the 0, 2, 5, 9, until like, sunod sila. Hindi, nag-rumble na like, nag-start sa 2, tapos next is 0. This is the shortest path na dapat nagkasunod-sunod like 0 to until the big number. Start at the 0 or small number until in the big number, until the 20. So this is the answer. This is the shortest path because this is the shortest path. This is the shortest path of each node from the starting vertex. So, guys, thank you for your watching or listening on this video.
Good day everyone, good day mom. Today I'll be discuss the problem number 2 of maximum and problem number 2 of shortest path. So first I'll be discuss the problem number 2 of maximum. So the problem is to find the maximum flow of computer network model below that transmit data from computer A to computer Z. So to solve this problem, the maximum flow in the network from source Z can be determined using a Ford-Fulkerson algorithm. So here are the steps to solve the problem. So the first step is initialize flow. Set all initialized flows in the network to 0. So the second step is find arguments paths. Use the depth first or the breadth first search to identify a path from A to Z, where additional flows is possible or the residual capacity greater than 0. So the step 3 is update flow. Adjust a flow along a augmenting path based on a minimum capacity. So the last step is to repeat or continue until no augmenting path exists. So the solution for this problem first is alteration or augmenting path A to B to D to G and to Z. So the path capacity is the minutes of 8, 9, and 8, 5 equals to 5.
So the second iteration, augmenting path A to C to F to H and to Z. So the path capacity, the 5, 4, and 5, 6 is equals to 4.
So the third iteration, augmenting path A to B to E to F to H and Z, is the path capacity of this is 39412 is equals to 1. So the maximum flow of the given network is 10 units.
Next problem is to find the shortest path of each node from the starting vertex. To solve the problem, finding the shortest path from the starting vertex to all other nodes is we can use Dijkstra's algorithm. So here are the steps of Dijkstra's algorithm. First is initialization. Set the distance to the starting vertex 0 as 0 and all other vertices as infinity. So next is mark all nodes as unvisited. Next, use a priority queue or similar structure to keep track of the next node to visit based on the shortest known distance. So the next steps is relaxation. For the current node, update the distance to each of its neighbors if it is shorter path is found.
So the third step is mark the current node as visited. Next, to move the unvisited node with the smallest tentative distance. Last steps is termination. Repeat until the nodes are visited or the shortest paths are found.
So here are the solutions. Step 1 is initialization. Starting vertex 0, initial distances is 0 and 7 infinities. So in step 2 is iterative steps. So the first visit is 0. Neighbors 1 quantity of 4 and 4 quantity of 11. So the update distances is 0, 4, infinity, infinity, 11, and 3 infinities. So the second visit 1, neighbors 2, quantity of 8, and 4 quantity of 11. So the update distances of it is 0, 4, 12, infinity, 11, infinity, infinity, infinity. So the visit 4 of it is, the neighbor is 5, quantity of 7. The update distances of it is 0, 4, 12, infinity, 11, 18, infinity, infinity. So in the visit 2, the neighbors of it is 3, quantity of 7, 8, quantity of 2. So the update distances is 0, 4, 12, 19, 11, 18, infinity, infinity. So in the visit 5, the neighbors of it is 6, quantity of 2, where the update distances is 0, 4, 12, 19, 11, 18, 20, and infinity. So the visit 3 is neighbors of it is 7, quantity of 9, 6, quantity of 14. So the update distances of it is 0, 4, 12, 19, 11, 18, 20, and 26. So in visit 6 is no update needed. So the final distances, the shortest path from node to other nodes is node 0 is to 0, node 1 is to 4, node 2 is to 12, node 3 is to 19, node 4 is to 11, node 5 is to 18, node 6 is to 20, and node 7 is to 28. That's be all. Thank you.
Good day. So let's find the maximum flow of the transfer network given below. So to start the problem, so let's proceed to the initialize of the graph. So the source node is S and the sink node is T. So we need to initialize it to 0. So the given network can be represented as a graph with a capacity on the edge. We'll initialize the flow for all the edge as 0, this, and the residual graph will initialize have the same capacity as the original graph. So here's the graph with the capacity. So this is the S to A is 8 and S to B is 10. Also the S to C is 6 and A to B is their capacity or their initialize is A and A to D is 7 B to C is their initialized is 6, and the B to D is their initialized is 6. Also, the C and D is ang initialized na is 5, and the C and E and their initialized is 12. Also, the D and E is their initialized is 4, and the D and T is their initialized and T is initialized to 11. So, let's find the augmenting path of the problem. So, using BFS, breadth first search, we look for a path for the source source S and the sink T where there is available capacity. So, let's start with the S and A. Their initialize is 8, and S and B and their initialize is 10, or their capacity is 10, and S and C is their capacity is 10. So their augmenting path is 10, 6, 13 equal to 6. So let's proceed to the update the residual graph. So we reduce the capacity along the path by the bottleneck capacity of 6. So S and B is 10, the initialized, and equal to 6, the augmenting path, which is this. Their augmenting path is equals to 4. The B and D is 6, equals to 6, so the residual graph is 0. And the D and T is 13 minus the 6 is the residual graph is 7. So we revise the capacity. If we revise the capacity for the possible flow of the backtracking, so we add the augmenting path, which is the 6. So this is the add. So the B and S is their capacity is add to 6, and the D to P is their add is 6, and also the T and D is add 6. So repeat augmenting path. So is, let's start with the S and A is 8, and the 6 and B is 4. Also the S and C is 6, and then the augmenting path or the repeated path is the 6, 7, 7 equals to 7. This is the repeated augmenting path. So to update the residual graph, so S A D to T by 7, which is the residual or repeated augmenting path. So S to A is 8 minus to 7 equals to 1, and also the A to D equals to their initial is or their capacity is 7 minus the 7 is equivalent to 0. Also the D to D, their initialize is 7, then minus to 0, and their equivalent is 0. So to first the capacity, so this is the reverse of the capacity. We add the repeat augmenting path, the result. So this is it. So another augmenting is S to A is 1 and S to B is 4. Also the S to 6 is 6. C is 6, the initialize. So S E E to T is 6, 12, 11, and then the augmenting or the initialize is 6. So to update the residual graph, let's start with the S to C, and 6 minus I equal to 6, which is equals to 0, and C and to E, their initializer, the capacity is 12 minus the 6 equals to 6 also, and E to T, their capacity is 11 minus the 6, which is naging 5 na lang. So, their termination is from S to B, then D and to T, which is 6, from S to A to D to T, which is 7, from S to C to E to T, which is 6. So their maximum flow is 6 add to 7 add to 6, which is the 24. So let's proceed to find the shortest path from the starting vertex to all the other vertices in the network graph below. So the vertice is A, B, C, D, E, and F. So the weight edge between vertex edge is A to B. So their distance is 2. So the starting node is A, which is initialized to 0, and the distance A is 0. So apply the algorithm. So the distance of A is 0, and the distance of B, C, D, E, F is infinity. So the unvisited nodes is A, B, C, D, E, F. So let's proceed to the shortest distance between the A, B, C, D, E. So the distance of or the initialized of A is 0, also the B is 2, the C is 4, and the D is 6, also the E is 8, and the F is 8. So let's proceed to the shortest path. So the shortest path is A to A to B, A to C, A to B and C, also the A, C, and E, A, B, D, and F. So, to find the shortest path in the network you provide, you would apply the algorithm starting from the specified vertex to the algorithm would enter determine the shortest distance and the path to all other vertices in the network. So that's all for the maximum flow and the vertex of my problem. Thank you.
Hi everyone, I'll be explaining how to solve a shortest path problem in a graph using Dijkstra's algorithm. This problem is all about finding the shortest distance from a starting node A to all other nodes in the given network. This report describes the application of Dijkstra's algorithm to determine the shortest paths from vertex A to all other vertices in a directed way graph. The solution minimizes path cost while traversing through weighted edges. The problem involves finding the shortest path in a directed graph. Dijkstra's algorithm is used due to its efficiency in handling graphs with non-negative weights. The shortest distance from A to all other vertices are A to B is equals to 2, A to C is equals to 4, A to D is equals to 3, A to E is equals to 9, A to F is equals to 6, A to G is equals to 5, A to H is equals to 9, A to I is equals to 8, and A to J is equals to 12. In conclusion, Dijkstra's algorithm efficiently computes the shortest paths in the graph, demonstrating its utility in network analysis and optimization problems. This report addresses the problem of determining the maximum flow in a network that transports oil from a tanker that node at to an oil tanker truck at node Z. The graph provided represents a network of pipelines where nodes represent junctions or points of transfer. Directed edge represent pipeline with associated capacities, maximum flow. The goal is to calculate the maximum amount of oil that can flow from A to Z while respecting the capacity constraints of the edges. Algorithm use Ford-Fulkerson method. The Ford-Fulkerson method is commonly used to compute maximum flow in a flow network. It uses the following steps. Start with an initial flow of 0 for all edge. Find an augmenting path from the source A to the sink Z with available capacity. Increase the flow along the path by minimum residual capacity of edge in the path. Repeat until no augmenting path exists. Step 1. Initialization. Set the initial flow along all edge to 0. Residual capacities are equal to the capacities provided in the graph. Step 2. Find augmenting path in update flow. Using the breadth-first search BFS to identify augmenting paths. First path, path A, path 1 to path 4 to path 7 is equals to Z. Bottleneck minimum capacity of 4, update flow along this path 4. Second path, path A to path 2, path 5, path 7 is equals to Z. Update the flow along this path by 2. Third path, path A to path 3, path 6 to path 8 to Z. Bottleneck 3, update flow along this path by 3. Step 3, calculate residual capacity. After updating flows, calculate residual capacities for all edge and check for more augmenting paths. Repeat until no further augmenting path exists. The final result is the total maximum flow from A to Z is 4 plus 2 plus 3 is equals to 9. In conclusion, the maximum flow of oil that can be transported from the tanker to the truck is 9 units. This was achieved by identifying augmenting paths and iteratively updating the flows while respecting edge capacities. This approach is efficiently and widely applicable in network flow optimization problems such as transportation systems, data networks, and logistics.